This is the feasibility report for water reuse in the International Wastewater Treatment Plant by the Seven Sewages. My name is Lene Leininger.
My name is Diana Rojas.
My name is Ferris.
My name is Colby Lau.
My name is Sebastian Asensio.
The outline of our report will cover 4 sections, including the introduction, which is going to be discussing the current challenges at the International Wastewater Treatment Plant, our upgraded nutrient removal design to aid in phosphorus and nitrate removal. And then we want to build an advanced water purification facility to include membrane filtration, reverse osmosis, UV disinfection, and advanced oxidation. Lastly, this project will cover some additional logistical considerations of this facility. Our site is near the Tijuana River, and currently the Tijuana River flows from Mexico into the river estuary in San Diego, California. The pollution is caused by the increased population, aging infrastructure, and industrial expansion within the Tijuana area. The current wastewater system capacity is around 25 MGD, and there's currently about 50 MGD, which leads to the system being overloaded. So now there's just free flowing into the river. The existing treatment for this facility includes screening, grit removal, chemically assisted sedimentation, activated sludge aeration, disinfection, and secondary treatment. Untreated wastewater currently overflows into the estuary. This results in a lot of beach closures and health risks for communities near the estuary. Wastewater systems must meet the discharge permit requirements since discharge is in California, even though the waste is from Tijuana, which makes this an international challenge. Climate change has also intensified rain, increasing unpredictable flows and sewer overflows. The current upgrade at the Tijuana treatment plant is to handle a peak flow of 75 MGD and an average flow of 50 MGD. The treated wastewater is currently discharged via the 11-foot diameter pipe, which is 4.5 miles long, into the Pacific Ocean. Project goal is to build a project for a small water reuse facility with an output of 20 MGD. The region is water scarce, and reuse would be highly beneficial in this area. In Baja California, around 70% of the water is used in agriculture, so recycled water could be used for landscape irrigation or groundwater replenishment. Some of the benefits of water reuse would be improve the soil quality, create green spaces, reduce air pollution, and improve infiltration, decreasing flooding and runoff. Some of the water reuse regulations, since this facility would be based in California, is that it must comply with the California Code of Regulations, Title 22, number 60301.230. Tertiary treatment effluent refers to water that has undergone advanced treatment following primary and secondary that can be used for water reuse. In order for a groundwater replenishment project, the project requires a 12-log reduction of viruses, 10-log reduction for Giardia, and a 10-log reduction for Cryptosporidium oocytes. This helps reduce seawater infiltration and mitigates the climate change effects. Some of the methods of groundwater replenishment include riverbank filtration and using groundwater wells. The regulations that regulate groundwater replenishment include Title 22, Article 5.1 for surface replenishment and 5.2 for subsurface replenishment. This includes standards such as pathogen control, wastewater source control, etc. Groundwater replenishment and landscape irrigation are valuable, sustainable solutions for addressing regional water challenges. Currently, it's not feasible due to the lack of wastewater control in Tijuana, which will be addressed later on. Other considerations for this project would include cost, politics, flow variability, which will all be covered in logistical considerations.
Well, for our design choice for the nutrient removal, we selected the Modified University of Cape Town, or the Modified UTC process. And this method is actually a really great fit for this project because it's really good at removing both nitrogen and phosphorus from the wastewater, which is, of course, is important for meeting water reuse standards. And here we can see that nitrogen is removed in a certain process, and the way it's removed is first, ammonium is in the water is converted into nitrate, which happens as a result of oxygen. And this step is called nitrification. Then in a zone without oxygen, special bacteria turns that nitrate into nitrogen gas, which is harmless and can simply escape into the air. And of course, the second step is called denitrification, and together they remove nitrogen from the water. So it's removing nitrogen completely from the entire system. And of course, apart from the nitrogen, we also have the phosphorus that we also have to remove. As we can see there in our tread lines, the phosphorus is removed in 2 ways, actually. So some bacteria in the systems are naturally able to take the phosphorus and store it or use it for themselves. And if more removal is needed, we can also add chemicals like alum or ferric chloride to help us take out the extra phosphorus. And of course, by doing these 2 things, it helps us to treat the water so it's safe to reuse for things such as irrigation or maybe from other forms of reuse. And it doesn't harm the environment and groundwater. And as we've seen here in the tread line, we can see the multiple components that make up this nutrient removal. So we can see the different treads. We see how we have 4 different tanks. We have the anaerobic, the anoxic, and the aerobic. So nitrogen is removed and as well phosphorus. So for more information and for more step-by-step, please refer to our report for that.
Right, moving on to advanced water purification design. The new plant treatment will consist of 4 treatments, being membrane filtration, reverse osmosis, UV disinfection, and advanced oxidation with an influent of roughly 25 million gallons per day and an effluent of 20 million gallons per day. And after the treatment, the new water could be used possibly for groundwater recharge.
For our membrane filtration system, we chose ceramic membranes due to their exceptional durability and ability to withstand high operating temperatures and pressures, which makes them ideal for this filtration system. Additionally, we also selected an outside-in configuration, which offers the advantage of maximizing surface area without compromising the inflow rate. Through our calculations, we determined that to filter 20 million gallons per day for irrigation, the system would require a feeding flow rate of approximately 24.6 mgd. And in order to handle such high volumes of water, we also established that the system would need an online production factor of 89.30%. From the table, we can also see that we would need a total number of 16 skids and require a total land area of 92 meters squared. It is important to also include that the membrane filtration system would provide a 4-log removal of pathogen credit, which effectively removes harmful pathogens such as viruses, Giardia, and Cryptosporidium.
For the reverse osmosis step of the process, the recovery rate is 90%, meaning 90% of the feed water becomes usable permeate and 10% becomes reject. This reject will be blended with the remaining secondary treated effluent. Additionally, this step will achieve a 6-log removal of viruses and other microbial contaminants, complying with California's Title 22 regulations for indirect potable reuse. Furthermore, with a target permeate flow of 20 megagallons per day, it was determined that the system will require a feed water flow of 22.2 megagallons per day and a membrane surface area of approximately 157,720 meters squared. This corresponds to about 4,853 reverse osmosis elements housed in about 693 pressure vessels. Given the standard dimensions of a pressure vessel being roughly 40 feet long and 8 feet in diameter, and allowing additional space for piping and maintenance access, each vessel is estimated to occupy about 90 feet squared. Therefore, the total land area required to accommodate the RO treatment unit is approximately 1.43 acres. For the arrangement, the design shows the reverse osmosis system in a 2-to-1 parallel configuration with 2 stages. The first stage will have 462 pressure vessels arranged in 22 rows with 21 vessels each. The second stage will include 231 pressure vessels organized into 11 rows of 21 vessels. Each stage will feature a permeate flow pipe to collect and remove the produced permeate from the system. All can be seen in the diagrams in the slide.
Moving on to UV disinfection. This will effectively inactivate bacteria, viruses, and other harmful microorganisms without the use of chemicals. The team was to determine the UV dose required for a 6-log inactivation of the MS2 bacteriophage virus, in which it was calculated to be 131.3 millijoules per centimeter squared, with a contact time of 26.26 seconds. This was calculated using the dose response curve shown on the right. It was calculated that 1,315 lamps were needed over 110 banks with a lamp intensity of 5 milliwatt per centimeter squared. Each bank will house 12 lamps, each lamp being 6 feet long and oriented 1 foot apart from each other's center lines. As you can see on the diagram on the bottom left, that makes for a bank that's 12 feet long and 5 feet wide, making one bank area 60 square foot. It's also recommended to leave 3 feet of space in between the banks to allow for maintenance and access. Orienting 110 banks by a 10 by 11 setup leaves us with 168 feet by 83 feet of total land area required, and that equates to almost 14,000 square foot or 0.3 acres.
Now moving on to the advanced water purification, we looked at how advanced oxidation process, or the AOPs for short, are useful because they not only kill the germs, but they also remove harmful chemicals from water, which of course is important in reuse. And this is important because some chemicals like 4-dioxane can be removed with just UV light alone. AOPs work by combining UV light with a chemical like hydrogen peroxide, which of course creates a powerful particle that breaks down the tough contaminants. And there's another method that uses UV light with free chlorine called UV-HOCl, which is where UV light decomposes hypochlorous acid, or HOCl. And As a result, studies have shown that UVHOCl works just as well as UV with hydrogen peroxide, and it might even use less energy and fewer chemicals. And of course, to see this research, please refer to our report that we can recommend that using this method as a better choice for advanced oxidation. Moving on to the landscape irrigation. Well, in Tijuana, we know that groundwater can be safely used to landscape irrigation. So to make sure this is done responsibly, it's important to regularly check the quality of the water and the level and looking for any harmful contaminants inside the water. As of course, we know that this protects the water source and it also can be used for long-term purposes. But of course, in order to do that, we also need to look at how much water is needed for that irrigation. And we looked at of course, the area's climate and the vegetation in that area. So in the Tijuana area, it's moderately dense in vegetation. There's water efficient vegetation, and it has a high microclimate factor. So using these three factors, we calculate the landscape coefficient of 0.24. And of course, this value can help us to estimate how much water is lost through evapotranspiration, which is how water evaporates from soil and plants. With this coefficient, we actually determine the hydraulic loading rate and the amount of water needed per year, which is, of course, we calculated at 309.9 millimeters, and it was required that we found it in meters, which came out to 0.39 meters per year. Then using a flow rate of 20 million gallons per day, we use that value to calculate the volume, which came out to 27.6 million cubic meters of recycled water that would be available per year. Around 8,913 hectares of land in Tijuana could be irrigated using recycled water. And these calculations help to design efficient systems that make the best use of recycled water without harming the soil or the groundwater.
Some of the logistical concerns about this project is the feasibility of this project. Since the project would be in California, but treating Tijuana's waste, this leads to an international border challenge. The U.S. regulations under Title 22, California Code of Regulations, Division 4, Chapter 3, set general guidelines for groundwater replenishment that must be followed in order to implement such a project. This includes things like feasibility studies, community consultations, a monitoring system design, and a legal and regulatory review, all of which would be nearly impossible to do across the border. Another aspect would be where the recharge wells would be located, as wells may need to be drilled in order to use groundwater replenishment. Third consideration would be who would be responsible for the regulations for this project. Some regulations that may be needed would be some industrial regulations where companies would have to clean their water before sending it to the wastewater treatment plant, but there is no U.S. enforcement authority in Mexico. Another aspect is who would pay for this project, since it would be a joint effort between Mexico and California. To establish viable monitoring, permitting, and legal review processes in Mexico would require substantial institutional cooperation and new legislation, which hasn't been developed yet. Below is the site plan of where our units would be located. As you can see, space is not something that is short near the International Treatment Plant. So you can see the legend and the site plan of where we would put our facility, which would be next door to the current wastewater treatment plant.
This design effectively supports all three pillars of sustainability as well. Environmentally, it protects the public health and ecosystems by reducing untreated wastewater discharges and preventing seawater intrusion through advanced treatment. Economically, it reduces reliance on costly imported water and offsets long-term costs by avoiding environmental fines and penalties. Socially, it improves public health by minimizing exposure to contaminated water and enables greener urban spaces in Tijuana. As a binational project, it also fosters U.S.-Mexico cooperation. In addition to promoting sustainability, this project advances several UN Sustainable Development Goals as well. It strongly supports SDG 6, clean water and sanitation, specifically sub-goals 6.3, 6.4, and 6.5, by improving water quality, increasing reuse efficiency, and enabling integrated water management through advanced treatment methods like membrane filtration, reverse osmosis, and UV disinfection. It also addresses SDG 11, sustainable cities and communities, particularly sub-goal 11.6, by reducing urban environmental impacts and improving water quality in both Tijuana and San Diego through expanded treatment capacity. Finally, the project fulfills SDG 12.12, responsible consumption and production, by treating wastewater as a valuable resource, promoting the efficient and sustainable use of water.
Addressing some recommendations to make all this feasible. The ideas that need to be addressed are the aging infrastructure, in which the existing international wastewater treatment plant systems are outdated and operating beyond their original design due to rising regional populations. A new facility must be properly integrated with current infrastructure, and treatment processes must be enhanced. And increased funding is also necessary to expand the international wastewater treatment plant's capacity and to improve its long-term operational resilience. Environmental protection is also very important and critical to preventing untreated wastewater from polluting the Tijuana River estuary and nearby coastal waters. International cooperation is also very essential, as cross-border regulatory agreements and collaboration are essential for effective implementation, long-term sustainability, and shared environmental responsibility. Thank you.